In 1949, a logician carried a birthday present into Einstein's office in Princeton. It was not a book, it was a universe. An exact solution to Einstein's own equations, describing a world where a traveler who only ever moves forward in time can arrive back at a moment they have already lived. Einstein read it and could find nothing wrong. What he wrote instead was that it would be interesting to see whether such things should be excluded on physical grounds. Somebody go and find the reason. 77 years later, nobody has. And when people went looking for why, what they found was not a reason to throw that universe out. It was a proof that the shape of our own universe cannot be determined by evidence, not by better telescopes, not by more time, not by every observation that could ever be made. By the end of tonight, you will know exactly what the greatest mystery in modern physics is, and why it might never be solved. Before we begin, if the quiet dismantling of something you were sure about is how you like to fall asleep, a like or a subscribe would mean a great deal. It keeps these long nights possible. Now, let's ease in. The strangest present anyone has ever given a physicist was a universe in which time runs in circles, and it was handed over as a birthday gift. The year was 1949. Albert Einstein was turning 70, and a collection of essays was being assembled in his honor, edited by a philosopher named Paul Arthur Shilp. The contributors were the obvious people: colleagues, students, admirers, the great names of the field, and most of them wrote what you would expect them to write: appreciations, reflections, careful assessments of a career that had rearranged the 20th century. One contributor did not do that. Kurt Godel, the logician, was by that point Einstein's closest companion at the Institute for Advanced Study in Princeton. The two of them walked home together most days, a pair of accented voices moving slowly down the same stretch of road, and Einstein is said to have remarked in his final years that he came into the Institute mainly for the privilege of walking home with Godel. So Godel had access. He had the older man's attention, and what he chose to contribute to the birthday volume was not an essay about Einstein's ideas. It was a new solution to Einstein's own equations. The solution described a universe, not our universe, a possible one, a rotating one, filled uniformly with dust and carrying a negative cosmological constant. It does not expand. It has no beginning in the usual sense, and running through every single event in it, without exception, is a closed time-like curve. That phrase is going to matter for the next 2 hours, so let me put it plainly. A time-like curve is the path of a massive object through space and time. Your path, right now, is one. It always moves forward. There is no reversing, no going backwards along it, no moment where the object's own clock ticks the other way. A closed time-like curve is a path exactly like that, always moving forward, 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 which nevertheless arrives back at an event it has already passed through. The geometry of the universe bends around in such a way that going relentlessly forward eventually brings you back. Godel had found this inside Einstein's equations, not by adding anything, not by breaking any rule, just by asking the equations what else they permitted, and writing down an answer they had been quietly holding the whole time. Imagine the room. It is Princeton, and the light coming through the window is the flat, particular light of late winter in New Jersey. The manuscript is on the desk between them. Einstein is nearly 70, and he has spent 34 years living inside these equations. And here is a page telling him something about them that he did not know. He reads, "The logician waits, the way logicians wait, without helping. And the thing on the page is not an error. That is what makes it difficult. There is no mistake to find, no term dropped, no sign flipped. The mathematics is exact. The universe described is a legal citizen of his own theory, holding a valid passport, standing at the border with all its papers in order, and inside it, a traveller who only ever moves into the future, can arrive at their own past. Einstein does not throw it out. He does not say it is wrong, because it is not wrong. What he eventually writes, for publication, in the same volume, is that Gödel's solutions constitute an important contribution, and that it would be interesting to weigh whether such solutions ought to be excluded on physical grounds. Excluded on physical grounds. Hold on to that phrase. We are going to come back to it more than once tonight, and each time it returns it will mean something a little heavier than it did before. Because here is what it meant in 1949. Einstein was not saying the model was impossible. He was saying that somebody was going to have to find a reason to get rid of it. That reason would have to come from physics, from some principle about how matter and energy and geometry actually behave, rather than from the simple fact that the model offends our intuitions about time. It was a request, a very reasonable one. Somebody go and find the reason. 77 years later, nobody has found it. That is not for lack of effort. An enormous amount of very serious mathematics has been done on exactly this question. Theorems have been proved about the conditions under which closed time-like curves can and cannot form, about what kinds of matter would be required to bend a region of spacetime around on itself, about whether such regions can be created rather than merely existing from the beginning. Whole literatures exist. Careers have been built inside them, and what has come out of all of it is not a knockdown argument. It is a long series of partial results, each one ruling out some particular route, none of them closing the door. It is worth noticing who the messenger was. 18 years before he handed Einstein that manuscript, the same man had proved that any formal system rich enough to do ordinary arithmetic contains true statements it cannot prove, a result that has been quietly rearranging people's expectations about knowledge ever since. And then, in 1949, he found a second boundary of the same family, this time not in arithmetic, but in the geometry of space and time. Nobody at the time seems to have described it that way, but it is a pattern, and it is going to repeat tonight. None of this, incidentally, means we live in Gödel's universe. We almost certainly do not. His model rotates and does not expand, and ours very clearly expands and shows no sign of any global rotation at all. The observations rule it out as a description of us. What they do not do, what nothing has done, is rule it out as a description of something. It remains a perfectly legitimate solution of the equations, sitting in the catalogue, waiting for the physical reason that has not arrived. There is a physicist and philosopher of physics at the University of California, Irvine, named J.B. Manchak, who works on precisely this material, and whose position on the question is about as modest as a position can be. He does not think time travel is possible. He does not think it is impossible. His view is that we do not know, and he finds it genuinely interesting that a claim that non-committal, a claim which amounts to a shrug, somehow reads to people as radical. Now, before we go any further, I want to disarm the obvious misunderstanding, because if I do not, it will sit in the back of your mind for the next 2 hours and quietly distort everything else. When physicists say that general relativity permits time travel, they are not talking about the kind you have seen in films. Going back and changing what happened is not something these models allow. There is no version of this where you arrive in the past and alter it, because there is no separate past sitting there waiting to be altered. What the geometry permits is much stranger and much quieter than that. It permits a path that closes, a world line that goes forward and forward and forward and meets itself. Everything on that path is consistent with everything else on it, because it is one path. It was always closed. Nothing gets changed, because there was never a version in which it went differently. And if you are wondering what happens to a person rather than a point particle, whether they would age indefinitely, whether entropy would pile up on them like snow, the model's answer is oddly undramatic. Whatever is going on with the matter is periodic. It comes back around to itself in exactly the way the particle does. Your body arriving at an event it has already occupied is in the same configuration it was in the first time, because there is no first time. There is only the loop. So that is where we begin. The most successful theory of space and time that human beings have ever produced contains, in its own solutions, universes in which time closes. The man who wrote the theory looked directly at one of them, could not find a reason to throw it out, and asked for help. And in the 3/4 of a century since, the request has gone unanswered. But this is not, in the end, a video about time travel. Time travel is the door. What is behind the door is much larger and considerably harder to live with, and it begins with a question that sounds almost too simple to be worth asking. What exactly do we mean when we say a model is part of Einstein's theory at all? There is no such thing as general relativity. There are a great many of them, and nobody knows which one is ours. I realize that sounds like a provocation, so let me build it slowly, because once you see how a model of Einstein's theory is actually assembled, the claim stops being provocative and starts being obvious. Start with the least interesting object in the whole business, the manifold. A manifold is a shape with one defining property. Near any point, it looks flat. Zoom in far enough on any part of it, and what you see is indistinguishable from ordinary coordinate space. The featureless grid you learned to draw axes on in school. A sphere is a manifold. Stand on a beach and the earth looks flat, which is precisely the property in question. A cylinder is a manifold. A donut surface, a torus, is a manifold. In general relativity, the manifold has 4 dimensions. It is smooth, meaning you can differentiate it as many times as you like. It is connected, meaning it is all one piece. And it has no boundary, meaning there is no edge to fall off. Each point in the manifold represents an event, not a thing and not a place, an event. Somewhere and somewhen, together, in a single indivisible package, this spot, this instant. Now here is the important thing about a bare manifold, and I want you to sit with it for a second, because it comes back later, in a form you will not see coming. A bare manifold has no way of distinguishing here from there. Every point is exactly like every other point. There is nothing at one location that is not also at every other location. If a universe were nothing but a manifold, it would be a river you could step into as many times as you liked, and it would be the same river every time, because there would be nothing about it that could ever differ. Onto that featureless shape you place structure. In general relativity, the structure you place is a metric, specifically a Lorentzian metric, smooth and non-degenerate. What the metric does, in practical terms, is attach a little light cone to every single point of the manifold, along with some additional information about how straight lines behave. The light cone at a point tells you which directions from that point are time-like, meaning something with mass could travel that way, which are null, meaning light travels that way, forming the cone itself, and which are space-like, meaning nothing can get there from here without exceeding the speed of light. The metric is what makes the geometry real. It tells you distances, angles, and above all, curvature, the curvature that we experience, at the bottom of a gravitational well, as weight. There is one more piece of vocabulary to plant here, because a great deal will rest on it later, and it is the difference between 2 ways of saying that 2 universes are the same. 2 spacetimes are called isometric if there is a smooth, reversible map carrying one onto the other and taking the metric exactly along with it. Isometric universes are not 2 universes. They are one universe, described twice, in different coordinates, the way a city is the same city whether you approach it from the north or the south. But there is a much weaker relation, and it is called local isometry. 2 spacetimes are locally isometric if every point in either one sits inside some neighborhood that matches a neighborhood in the other. Not the whole thing matching the whole thing, just every small piece finding a partner somewhere. 2 universes can be locally isometric, every neighborhood in one having an identical twin in the other, while being globally, structurally, entirely different objects. The gap between those two relations is small enough to state in one sentence, and large enough to hold everything we are going to find tonight. So far, so standard. A manifold with a metric on it. Now comes Einstein's equation, and this is where the picture most people carry around turns out to be wrong. The picture most people carry around goes something like this. Einstein's equation is a strict condition. Most conceivable geometries fail it. The ones that pass are the solutions, and the solutions are what the theory permits. Reality is filtered through a very fine sieve, and only a handful of universes get through. That is not what happens. Hand a specialist any Lorentzian metric you like, any one at all. Draw it out of a hat. Invent it. Make it as ugly and arbitrary as you please. They can use Einstein's equation to read off a matter field that satisfies the equation exactly, because the equation relates geometry on one side to matter and energy on the other. And if you have specified the geometry, you can simply run the equation in reverse and define the matter field to be whatever that geometry demands. The sieve does not filter anything, because you can always manufacture the thing that fits. Which means that talk about solutions to Einstein's equation is, on its own, an empty concept. Vacuous. Without constraints, the equation does not do anything. It has no content. The content arrives only when you add conditions. You say, I do not want any old matter field. I want one that satisfies certain energy conditions. That the energy density is not negative. That energy does not flow faster than light. That matter behaves the way we have observed matter to behave. Or you say, I am only interested in vacuum solutions, where there is no matter at all. It is those constraints that give Einstein's equation its teeth. Without them, the equation is a definition rather than a claim. And now, you can see the shape of the problem. The standard collection of models of general relativity, at its most permissive, is just the collection of all four-dimensional manifolds that admit a Lorentzian metric. All of them. Every geometry anybody could ever write down. They all satisfy Einstein's equation, in the minimal, contentless sense. And which subclass of that enormous population counts as the actual theory? That is up to you. You could restrict by local conditions, energy conditions, vacuum solutions, conditions that hold in each small neighborhood. You could restrict by causal conditions, no closed time-like curves, or the stronger requirement that the causal structure survive small perturbations, or the stronger requirement still that we will come to shortly. You could restrict by ruling out certain kinds of singularity. You could restrict by requiring that the universe be as large as it can possibly be. Each of these choices produces a different collection of models. Each different collection is, in a real sense, a different theory. This is what it means to say there is no such thing as general relativity. When a theorem is proved in this field, it is proved relative to a background collection of models. Change the background, and the theorem may become false, or unproven, or meaningless. Ask whether the theory is deterministic, and the honest answer is another question. Deterministic relative to which collection? Ask whether the theory forbids time travel, and again, relative to which collection? You will get different answers depending on which one you are looking at, and all of those answers can be perfectly correct. Manchak's stance on this is what he calls a pluralistic view, and it is worth stating carefully, because it is not skepticism, and it is not relativism. It is not the claim that anything goes. It is the claim that the interesting work consists of relative results. Assume the background possibility space looks like this. What follows? Assume it looks like that. What follows? We have accumulated an enormous number of these relative results, and they are genuinely informative. What he resists is the next step, the one that feels irresistible. But which is the real one? Which collection is the actual general relativity? His answer is that the question is a little misguided, because we are never going to be in a position to get at it. If somebody shows up insisting that general relativity is just one thing, the response is a puzzled scratch of the head and a question, where did that come from? Which is a question we are going to hear again in a considerably more uncomfortable context before the night is out. But before that, we need to see how the pruning is actually done, because everybody agrees that some models have to go. Nobody thinks a universe made of glued together scraps with holes torn in it is a serious candidate for reality. Physicists throw models out constantly, and they are right to. The question is what they are using to do the throwing, and the answer, when you look at it directly, is not quite what you would expect from a science. Every physicist working in this area agrees on one thing: some of the models have to go. You will not find anyone who believes that all of the standard solutions of general relativity describe physically reasonable universes. The idea is absurd on its face, and nobody defends it. So everyone agrees that the real theory, whatever it turns out to be, is some subclass of the full collection. There is a bouncer at the door, and there needs to be one. The disagreement that has never been resolved and shows no sign of resolving, is about what the bouncer is checking. Let us look at one criterion in detail, because it is representative, and because the answer is not what a person outside the field would guess. The criterion is called spacetime maximality. Put simply, it says the universe is as big as it can be. Some models of general relativity are extendable. You can attach more spacetime to them, continue the geometry outward, make them larger, and the result is still a perfectly good solution. Physicists look at extendable models and say, reasonably enough, on the face of it, that those are not physically reasonable. A universe that could have been bigger and simply stops feels wrong, feels arbitrary, feels like an artifact. Ask why, and follow the justification back to its source, and you arrive in the 1960s, in what people in this field call the Golden Era, when Roger Penrose and Robert Geroch and a handful of others were building the modern global analysis of spacetime from scratch. Read the original justifications for maximality that those people wrote down, and what you find there is not physics, it is metaphysics. Specifically, it is Leibnizian metaphysics. The principle, running back through the 18th century, that nature does not leave possibilities unrealized. Why would nature stop when nature could keep building? She would not. So she keeps building. Therefore, extendable models are unreasonable, because that is not how nature works. Now, I want to be careful here, because it is easy to make this sound like an accusation, and it is not one. That argument has a distinguished pedigree, and it captures something real about how physicists think. It is not stupid, but it is also not a measurement, and it is not a derivation, and it is not a consequence of the field equations. It is an intuition about the temperament of the universe, imported from philosophy, doing load-bearing work inside the definition of a physical theory. And when Manchak, who has been chewing on the question of what makes a manifold physically reasonable for something like 20 years, looks hard at these justifications, what he finds, over and over, is that they are not what they appear to be at first glance. You examine them closely, and they come apart in your hands. So the honest question to put to the bouncer is the one we are going to keep returning to tonight. Where does that come from? And there is a consequence to kicking models out that almost nobody anticipates, which is that you cannot do it for free. When you remove models from the collection, you have changed the space of possibilities. Every theorem in the theory that quantifies over possibilities, every statement of the form, for every spacetime such and such, or there exists a spacetime where, is now a statement about a different set of objects, and has to be asked all over again from the beginning. Take Geroch's own theorem from 1970 that every spacetime has a maximal extension, perfectly true, relative to the standard collection. Now throw out the unreasonable models, as, by hypothesis, you must, since they are unreasonable, and re-ask the question, inside this new variant of the theory, Does the theorem still hold? It is simply not clear, and in some cases you can show something considerably worse, that nature does not even have the option of building a maximal universe, because every route to one runs through territory you have just declared forbidden. You will see exactly such a case tonight, and it involves a fractal. This is the Pandora's box. You reach in to tidy up the theory, and the theory's entire modal structure shifts underneath you. Maximality is only one criterion. Here is another, and it is more intuitive. Take Minkowski spacetime, the flat, empty, perfectly well-behaved spacetime of special relativity, the simplest and most respectable geometry in the whole subject. Now remove one point from it, just one. Delete a single event. What you are left with is a model of general relativity. It is a legal solution, and it has a singularity in it, a place where the geometry has a puncture, where world lines run out of universe, and anybody looking at it will say, reasonably, that this is unphysical. What is causing that thing? There is no matter there. There is no curvature blowing up, no collapse, no mass concentrated anywhere. It is not a singularity that anything produced. It just appeared out of nowhere, because somebody deleted a point. Geroch, in the 1970s, was among the first to look at solutions like that, and conclude that the theory needed a condition to rule them out. What he came up with is called whole freeness. Others, Hawking, Ellis, and more since, have proposed their own versions, which is itself part of the problem. There are multiple, non-equivalent ways of formalizing the idea, and they do not agree with each other. A quick warning about vocabulary, because this trips up everybody. These wholes have nothing at all to do with Einstein's famous whole argument from 1913, which is an entirely separate and much discussed puzzle about coordinates and identity. Different idea, same unfortunate word. Manchak has said outright that the whole argument should not be called the whole argument, because it is not really about a whole. But the name is 113 years old now, and nobody is going to change it. And here is what makes the whole condition genuinely hard, rather than merely fiddly. You cannot simply outlaw all singularities. The singularity theorems of the 1960s, Penrose in 1965, then Hawking, then the two of them together, proved that under very general and very reasonable conditions, singularities are forced. They are not optional. So the theory is stuck admitting some singularities as physically respectable while wanting to exclude others as artifacts. And the field equations do not tell you which is which. That judgment has to come from somewhere else. And if you want a reason to be humble about these judgments, the history supplies one. In 1939, Einstein published a paper arguing that Schwarzschild singularities do not exist in physical reality, that the objects we now call black holes were mathematical artifacts, not features of the world. He was wrong. We have since photographed the shadow of one at the center of a galaxy 55 million light-years away, and heard two of them collide. The judgment that a solution is too strange to be real has been made before by the most careful person in the field, about the most famous objects in modern astrophysics, and it did not hold up. That is worth remembering every time someone declares a model pathological on the basis of how it feels. Between the very permissive conditions and the very strict ones, there is a middle rung worth naming, because it comes up later. It is called stable causality, and it asks not merely that a space-time contain no closed time-like curves, but that you could not create one by nudging the geometry a little. A universe can be free of time loops in a fragile way, sitting on a knife edge, one small perturbation from developing them. Stable causality demands that the freedom be robust. It is a good condition. It is also, like the others, a choice. Even the energy conditions, which feel like the most solidly physical constraints on the list, turn out to be softer than they look. They are meant to encode the idea that matter behaves the way matter behaves. Positive energy densities, no energy streaming faster than light, and several of them are known to be violated by perfectly ordinary quantum fields in perfectly ordinary situations. So the constraint that gives Einstein's equation its content is itself something we know is not universally true. Line all of this up, and a picture emerges that is quite different from the one most of us were handed. There is a theory. It admits an enormous population of models. Some subset of them describe physically possible universes, and the rest are mathematical debris. Nobody disputes that. But the tools we use to sort the debris from the universes are a mixture of well-motivated physical requirements, formalizations that disagree with each other, conditions known to have exceptions, and, at the foundations, an 18th century intuition about what nature would bother to do. Which brings us to something you have believed your whole life, that is not true, and that stopped being true for exactly this reason. Almost everyone who has ever heard of classical physics believes the same thing about it. Give me the complete state of the world at one instant, plus the laws, and the future follows. Every position, every velocity, every field value, and then the machinery grinds forward, and there is exactly one way the story can go. That belief has a name and a date. In 1814, Pierre-Simon Laplace described an intellect that knew all the positions and all the forces at a single moment, and was powerful enough to analyze the data. For such an intellect, he wrote, nothing would be uncertain. The future, like the past, would be present before its eyes. We call it Laplace's demon, and it has been the emblem of classical physics for 2 centuries. Quantum mechanics is supposed to be the thing that broke it. Classical physics, we are told, was deterministic, and then the 20th century arrived and ruined everything. That story is not right, and what is interesting is not that it is wrong, but why. To see it, we need 3 pieces of vocabulary, and I am going to lay them out slowly, because everything else in this part is built on them. The first is a Cauchy surface. Picture a surface cutting across the universe. A slice, a snapshot, a moment. It is space-like, meaning no 2 points on it can influence each other. And it has one further property, which is the property that matters. Every causal curve in the entire space-time, if you extend it as far as it will go in both directions, must cross this surface somewhere. Not most of them, every one, which means that everything happening anywhere in that universe registers on this slice. Nothing can sneak past. Nothing can arrive from a direction the slice does not cover. It is a complete instant. The second piece of vocabulary is a name for having one. A spacetime that possesses a Cauchy surface is called globally hyperbolic. One that does not is not. And that is a real distinction with real consequences, because not every spacetime has one. The third piece is what happens when you do not. Take a surface, put your initial data on it, and evolve the data forward, using the field equations. In some spacetimes you can keep going as long as you like. In others, you evolve up to a certain boundary, and past that boundary, the evolution simply stops. The data on your surface no longer determines what happens. That boundary has a name. It is called a Cauchy horizon. And I want to be precise about what a Cauchy horizon is, because the definition is subtler than it first sounds. A Cauchy horizon arises when it is possible to extend the spacetime further, but not in a way that keeps your surface a Cauchy surface. So the procedure is this. Put data on a surface. Evolve it as far as you can. If you reach a point where you cannot extend at all, you are in a globally hyperbolic spacetime, and your surface was Cauchy after all. But if you can extend further, and every possible extension destroys the global hyperbolicity, every one of them ruins the property, then what you have hit is a horizon. Past that horizon, the equations do not tell you what happens next. And notice there is no probability distribution to fall back on. This is classical physics. There is no wave function, no Born rule, no statistical spread. There is just a boundary, and on the far side of it, the theory declines to say. Now, the reason this matters, There are deep results, the work of Yvonne Choquet-Bruhat and Robert Geroch from the late 1960s, showing that data on a Cauchy surface can be evolved forward in a unique way, producing what is called the maximal globally hyperbolic development. That theorem is the precise sense in which general relativity is deterministic, Laplace's demon made rigorous. But look at what the theorem assumes. It assumes a Cauchy surface. It assumes global hyperbolicity, and global hyperbolicity is not something the theory hands you. It is something you impose. Roger Penrose introduced a hypothesis to cover exactly this, and Robert Wald's textbook gives it perhaps its cleanest formulation. The strong cosmic censorship hypothesis says, all physically reasonable spacetimes are globally hyperbolic. Read that sentence one more time, with the last few parts in mind, and you can see the entire mechanism. Whether cosmic censorship comes out true depends on how large your collection of physically reasonable spacetimes is. Make the collection small, throw out everything with awkward behavior, and censorship is true because you have removed the counterexamples. Make it liberal, let in the misfits, and censorship is false because the misfits are the counterexamples. That is what the whole literature is doing. The people proving censorship theorems are making assumptions that pare the collection down, keeping the riff-raff out. The people producing counterexamples are being more permissive, letting more models in, and those models are the counterexamples. Both camps are doing perfectly good mathematics. They are answering different questions and calling them the same question. Manchak's assessment is blunt. We are never going to get to the answer of whether censorship is true, because that is how the game is set up. So here is what actually follows, and it is the first thing tonight that I think is genuinely difficult to hold. It is technically false to say that classical physics is deterministic, not approximately deterministic, not deterministic outside black holes. False, as stated. General relativity is deterministic relative to a collection of models that has been curated, in part, precisely so that it comes out deterministic. Relative to the full standard collection of models, it is not. You can say the theory is deterministic if you first remove all the models, demonstrating that it is not. And of course you can. Anyone can. But then the determinism is a property of your list, not of nature. And none of this has been hidden. It has been sitting in the open literature for decades, discussed by everyone in the field, uncontroversial among specialists. It is simply not what any of us were told. The most famous property of the classical world, the one that generated 3 centuries of argument about free will, the one that quantum mechanics is supposed to have overthrown, turns out to have been, in part, a decision about which models to put on the list. Nobody hid it. It just did not make it out of the seminar room. There is a cousin of this in Newtonian mechanics, and it is worth a moment because it shows the pattern is not a quirk of relativity. John Norton constructed a dome, a specially shaped surface, with a particle sitting at rest on the very top of it. Under Newton's laws, with no push and no cause of any kind, that particle can spontaneously begin to slide at any arbitrary later time. The mathematics permits it. You can restore determinism by adding a technical requirement, a smoothness condition on the forces, called Lipschitz continuity, and people do. Norton's reply is that the restriction begs the question. You have assumed determinism in order to prove determinism. Manchak notes a real difference between the two cases, and it cuts in an uncomfortable direction. Norton's dome is a non-standard piece of Newtonian mechanics, because the dome's surface is not smooth in the ordinary way. You have to go slightly outside the usual framework to build it. The general relativistic indeterminism is not like that. It requires nothing exotic and nothing added. It happens entirely inside the standard collection of models. You do not have to leave the theory to lose determinism. You only have to stop leaving things out. And these are not fringe geometries either. the interiors of the rotating and charged black hole solutions, the Kerr and Reissner-Nordström metrics, textbook objects, the standard description of essentially every real black hole in the universe, since all of them rotate. Both contain Cauchy horizons. Fall into one, and there is a surface beyond which the physics on the outside does not determine what you find. That is the second time tonight that something has come apart under inspection. The first was the idea that Einstein's equation, on its own, says anything. The second is that the classical world runs on rails. Both came apart for the same reason: a choice about which models count, made for reasons that were not quite physics. Now hold that in mind, because we are about to ask the same kind of question about something much larger, not whether the future is fixed, whether the shape of the universe is knowable at all. And for that we need to go back to 1977, and a conjecture that sat unproven for a very long time. There is a universe where the problem we are circling becomes concrete, and it is not an exotic one. It may well be a rough description of the one you are lying in. In flat Minkowski spacetime, an observer's past light cone opens without limit. Wait long enough, and it swallows everything. There is no event anywhere in that universe that will not eventually fall inside your view, if you are only patient enough. Given infinite time, an observer in flat spacetime sees the whole thing. De Sitter spacetime does not work that way. De Sitter spacetime is the maximally symmetric solution with a positive cosmological constant, an empty universe undergoing eternal accelerated expansion, first written down by Willem de Sitter in 1917. And in de Sitter spacetime, the light cone does not open without limit. It has asymptotes. It runs up against a wall and stops. There is a finite region an observer can ever see, and no amount of waiting enlarges it. The horizon does not retreat as you approach it. It simply sits there, and everything beyond it is permanently outside your reach. So consider an observer in de Sitter spacetime. Their entire observational past, everything they have ever seen or could ever see, from any moment of their existence, is a proper part of the universe, not the whole of it. And here is the consequence. That observer cannot tell whether they are in de Sitter spacetime, or in a version of de Sitter spacetime that has been unrolled, or in one with holes cut into it somewhere out past the horizon, or in any of the indefinitely many other geometries that agree with de Sitter inside the visible region and differ everywhere outside it. All of those universes look identical from where they are standing, not similar, identical. Now, the reason this is not an academic curiosity: in 1998, two independent teams measuring distant supernovae found that the expansion of our universe is accelerating. That result was confirmed many times over, and it earned a Nobel Prize in 2011. And an eternally accelerating universe approaches de Sitter geometry. On the largest scales, in the far future, that is what our universe is heading toward. Which means the horizon behavior I just described is not somebody else's problem. It is, on some level, likely to be ours. Right now, there are galaxies whose light will never reach us, not because they are too faint, not because we lack the instrument, but because the space between us and them is expanding in a way that light cannot cross. The set of things we could ever, in principle, observe is finite, and in the relevant sense it is shrinking. David Malament used exactly this example to introduce the problem in a paper published in 1977, and it is still the right way in. Show somebody a concrete, respectable, physically motivated spacetime in which an observer provably cannot determine which universe they inhabit, and only then ask the general question: how far does this go? Malament's paper gave the general question a precise shape, and the definition is the hinge of everything that follows tonight. He called it observational indistinguishability, and it goes like this. One spacetime is observationally indistinguishable from another if, for every point in the first, there is some point in the second whose observational past is exactly the same shape, isometric, identical as a geometry. Unpack that, and here is what it says. If universe A is observationally indistinguishable from universe B, then an observer standing anywhere at all in A cannot know which of the two they are in, anywhere, not just at some awkward vantage point, not just early on before the light has arrived. Every point in A has a counterpart in B with an identical view. No observation they could ever make, even in principle, distinguishes the two. This is not a claim about missing data. It is a claim about data that cannot exist. Malament noticed one exception, and it is a strange one. Suppose a spacetime contains a point whose observational past is the entire universe. A single event from which absolutely everything is visible. Every place, every moment, all of it. Manchak calls these causally bizarre spacetimes. You and I can think of them as universes containing a God point, and we are going to come back to them, because they are one of the most peculiar objects in this whole subject. In a universe like that, the epistemic problem simply does not arise. You can see everything, so of course you know where you are. Malament's conjecture was that this is the only exception, that every space-time which is not causally bizarre has a counterpart, a distinct, genuinely different universe, not merely the same one in different coordinates, from which it cannot be observationally distinguished. He did not prove it. What he offered was an argument sketch, and it acquired a nickname, the clothesline construction. Here is the picture. Take a countable sequence of points in your universe, chosen so that their observational pasts, all put together, cover the whole thing. Such a sequence always exists. That is established, not assumed. Now imagine those observational pasts as items of laundry, and string them out along a line, embedding each one, separately and without overlap, into some new spacetime. Between them you put filler geometry, and the filler is subject to almost no constraint at all. It just has to keep the metric smooth. With that much freedom, you can obviously make the new universe globally different from the old one, and yet every point of the original sits inside one of the strung-out pieces, so every observer in the original has a counterpart in the new one with an identical view. Nothing observable has changed. Everything else has. It was a lovely argument. It looked right. Everybody in the field believed it, and it was not a proof. It sat there as an open conjecture for 32 years, long enough for the graduate students who first read it to become professors, and for some of them to retire. The problem, incidentally, had been circling for a few years before Malament wrote it down. Clark Glymore had raised closely related questions in 1972 and again in 1977, in papers about topology, cosmology, and convention. Glymore's version of indistinguishability was symmetric, each universe indistinguishable from the other, both directions. Malament's is weaker and asymmetric, running only one way, and it is Malament's weaker version that all the later theorems use. That detail sounds like bookkeeping, and it is not. A weaker premise makes a stronger result. It is worth saying something about the man who left it there, because his way of working explains a great deal about what eventually happened. David Malament, who is also at Irvine, and who is now in his 80s, is described by those who learned from him as having a distinctive and almost austere style. He is not drawn to fancy machinery. What he does is take a question that is confusing, a genuinely philosophical question, the kind that generates centuries of argument, and make it precise, using the formalism of general relativity, and then go to work, try to prove the conjecture, or find a counterexample. For him, the theorem is the philosophy. There is no separate stage where you explain what it all means. His best-known result works exactly that way. Stephen Hawking and others had shown that if two spacetimes have very rich, very well-behaved causal structures, and those causal structures are the same, then the topologies must be the same too. Tell me which events can causally influence which other events, and I will tell you the shape of the universe. Malament, as a graduate student, asked the obvious next question, which nobody had asked. How low can you go? How scarce can the causal structure be before the result fails? And he pushed the theorem down to a far weaker condition than anyone had managed. That 1977 paper is now the foundation of an entire approach to quantum gravity, in which you sprinkle discrete causal events into spacetime and let the geometry emerge from the causal relations among them. He did it again later with rotation. In Newtonian mechanics, rotation is unambiguous. In general relativity, it turns out you can write down several inequivalent criteria for what it means for one object to rotate around another, and Malament showed that they come apart. There are spacetimes where an object is rotating by one criterion and not by another. Rotation in general relativity is a subtle and non-unique business, and we know that because somebody formalized the philosophical question instead of arguing about it. So that is the state of things as the 1970s close. A definition, a conjecture, a sketch on a blackboard, and 3 decades of nobody managing to turn it into a proof. And then, in 2009, somebody did, and made it very much worse. Before I tell you what was proved, I want you to try something, because the thought experiment is the shortest route into it. Imagine an eye at every event in the universe. Not just everywhere, every when. An eye here in this room tonight. An eye in the corona of a star that has not formed yet. An eye at the bottom of the ocean 400 million years ago, and one on the far side of a galaxy whose light will never reach us, and one at every point along every path between them. Every location, at every moment, in the entire history of the cosmos, past and present and future, occupied by an observer who sees everything their vantage point permits them to see. Now imagine all of them reporting, every observation, from every eye, at every event, relayed back and gathered into one place. Not a survey, not a sample, the complete observational record of the universe, with nothing left out, because there is nowhere left to look from. You are holding, in your hands, all the evidence that could ever exist. Not all the evidence anyone has gathered, all the evidence there is. Every fact about the universe that could ever, even in principle, be observed by anything. And now someone takes the pile from you, goes into a back room, and comes out holding a different universe. Not a slight variant. A universe with a different global shape, a different topology, a different structure at the largest scale, and it produces every single one of your observations. Every eye, at every event, sees exactly what your eyes saw. Nothing you have contradicts it. Nothing you could add would contradict it, because there is nothing to add. The evidence does not distinguish them, and it never will. That is the theorem. Now here is how it actually reads. The paper is called Can We Know the Global Structure of Spacetime? It was received on the 26th of March, 2008, revised on the 28th of June, and published in a journal called Studies in History and Philosophy of Modern Physics, Volume 40, in 2009. It occupies pages 53 to 56. That is 4 pages. The most far-reaching statement anyone has made about the limits of what we can know about the shape of the universe fits on 4 pages, and there is not a wasted sentence on any of them. It does 2 things. First, it proves Malament's conjecture. After 32 years, the clothesline is a theorem. But that is the smaller half, and Manchak is careful to point out that people routinely miss the larger one. The second thing the paper does is strengthen the result far past what Malament had conjectured, and it is the strengthening that does the damage. Here is the statement, close to the paper's own words. Let a spacetime be any spacetime which is not causally bizarre, satisfying any set of local conditions. Then there exists another spacetime, not isometric to it, a genuinely different universe. such that the second one satisfies the same set of local conditions, and the first is observationally indistinguishable from the second. Any set of local conditions. Not some. Not a specific list the author has in mind. Any. I need to make sure the word local is doing its work for you here, because everything turns on it. A condition on a spacetime is called local if it survives local isometry. Remember that relation from earlier, where every small neighborhood in one universe has an identical twin somewhere in the other. If a condition is the sort of thing you could check by examining small patches, it is local. And now look at what that covers. Einstein's equation with a specified matter source is local. The energy conditions are local. Being a vacuum solution is local. Essentially, every constraint a working cosmologist would think to impose, everything that expresses the idea that the laws of physics as we measure them here also hold over there, all of it is local. So put it in the terms that matter. Take every local law of physics you have ever verified. Not just here, everywhere, at every point of the universe. No exceptions. Exactly as measured. Impose all of it. Demand that the Nemesis universe obey every one of them. And the theorem says, fine, here is your Nemesis universe. It obeys all of them, everywhere, and it produces every observation any observer could ever make in yours, and it is a globally different universe. The construction that does this is a chain, and the mechanics are almost embarrassingly hands-on. Start with the countable set of points whose observational pasts cover the manifold. For each one, find a point that lies outside its observational past. A small lemma in the paper guarantees such a point exists, and takes about 3 lines to prove. Take a neighborhood around that outside point, disjoint from the observational past. Inside each of those neighborhoods, place 2 closed 3-dimensional space-like surfaces. Now take copies of the original manifold, and in each copy, cut along those surfaces. Then glue the upper edge of a cut in one copy to the lower edge of the corresponding cut in the next copy, and the lower edge to the upper edge. Piece 1 attaches to piece 2, which attaches to piece 3, and on, indefinitely, in a chain. What you get is a legitimate spacetime. Every neighborhood of every point in that chain is isometric to a neighborhood in the original, which is exactly why it satisfies every local condition the original satisfied. And each original observational past survives whole, intact, sitting inside one link of the chain, which is exactly why no observer notices. The universe has been cut into pieces and reassembled into a completely different global object, and from the inside, at every single point, nothing has changed. One detail of that gluing is worth pausing on, because it is where the strangeness physically lives. When you excise a 3-dimensional disk and re-identify the edges, the 2-dimensional sphere that formed the boundary of the disk is necessarily left out of the resulting spacetime. It is not glued to anything. It is simply gone, which means the chain universe genuinely has punctures in it, real singular structure, at the seams. And that is a large part of why nobody claims it is a candidate for reality. It does not need to be a candidate for reality. It only needs to be legal and unobservable, and it is both. And I want to be exact about one phrase in the theorem, because it is doing more work than it appears to. The Nemesis universe is not isometric to the original. That is not a small technical caveat. 2 isometric spacetimes are not 2 universes at all. They are the same universe written down twice in different coordinates. The way a page of music is the same music whether you write it in one key or another. The theorem is not saying that you cannot distinguish a universe from a relabeled copy of itself. That would be trivial and uninteresting. It is saying that you cannot distinguish it from something genuinely, structurally other. This technique is not new, and its pedigree is worth knowing. Cutting and pasting spacetimes was introduced by Penrose, used extensively by Geroch, and appears in Hawking and Ellis's textbook. You take a well-behaved model like Minkowski spacetime, cut slits in it, glue the edges in some other arrangement, and produce wild topologies that are nevertheless perfectly legal models of general relativity. And the people who developed the technique were explicit about why. The point was never to exhibit a plausible model of our universe. The point was to produce counterexamples, to have, in a mathematical subject, the same thing that logic has, an object whose existence refutes a line of reasoning. Manchak's conclusion in the paper is one sentence, and it is delivered without any drama at all. There seems to be a robust sense in which the global structure of every cosmological model is underdetermined. Every cosmological model, not some pathological subclass. Every one, apart from the causally bizarre. There is a coda in the paper worth mentioning, because it forecloses the first objection a physicist would raise. One might argue that observing matter fields, actual stuff, not just geometry, would break the tie. Two universes with identical geometry might differ in their contents, and we could tell them apart that way. Manchak addresses it directly. The clothesline construction rules out objections of that kind, and Malament had already handled the point in his original paper. The acknowledgements list Geoffrey Barrett, John Earman, Robert Geroch, Clark Glymore, John Norton, and Kyle Stanford, with special gratitude to David Malament, whose sketch was the scaffolding and who is thanked by name for his help and encouragement. Malament conjectured it, Manchak proved it, and then went considerably further than the conjecture had gone. And here is the thing about the paper that I find hardest to get past. 4 pages. Manchak's stated working principle is that he does not put a sentence in a paper unless it is necessary, and does not put a word in a sentence unless it is necessary. His papers run 2 or 3 pages, which is extraordinarily unusual in philosophy, and short even by the standards of physics. He lets the result speak for itself. He does not add commentary about what it means. The theorem is the philosophy, which leaves the rest of us to work out what it means. And the first thing almost everyone tries is an objection that sounds completely reasonable, that I suspect you may already be forming, and that does not survive contact with the strengthened version. The objection goes like this, and I want to state it properly in its strongest form, because it is a good objection, and most people arrive at it on their own within about 30 seconds. Of course, the data does not deductively force a unique model. Nobody ever thought it did. That is not how science works, and it never has been. Science does not proceed by deduction from observations to theories. If it did, it would have stalled in the 17th century. Science works by induction. You tell me what the local structure of the universe is like here, in the region I can examine, and even though I cannot observe what is happening over there, I extrapolate. The laws of physics are not going to be completely different somewhere else. Whatever holds here, holds there. I do a little induction, I project the local onto the global, and I get my picture of the universe. That is the whole method, and it works, and demanding deductive certainty is a philosopher's game that has nothing to do with the practice of science. It is a fair objection, and the 2009 strengthening exists precisely to close it. Because here is what the theorem grants you. Give me all of your data, every observation from every eye, at every event, the complete record. And then, on top of that, I will allow you any kind of local induction you want. Assume the local laws hold everywhere. Assume the energy conditions hold everywhere. Assume it is a vacuum solution everywhere, if you like. Assume every local property you have ever verified holds at every point of the universe, without exception, forever. You still cannot pin down what the universe is like. That is not a rhetorical flourish. It is the content of the phrase, any set of local conditions. The Nemesis universe satisfies your uniformity assumption. It satisfies it perfectly, and it is still a different universe. There is a line the cosmologist George Ellis wrote in 1975, which Manchak quotes in the paper, describing the assumption every cosmologist has to make. that the normal physical laws we determine in our spacetime vicinity are applicable at all other spacetime points. Ellis was one of the first people to write seriously about the limits to verification in cosmology, and he returned to the subject in 1980 and again in 2007. The theorem's answer to his assumption is not that the assumption is wrong, it is that granting it does not help. You can have the uniformity principle, free of charge, and you are no closer. So what is left? There is exactly one exit, and it is a strange one. You can escape the theorem by doing a global induction, by assuming, outright, some property of the universe as a whole. Assume it is globally hyperbolic. Assume it has no holes. Assume it is maximal, as big as it can be. Any of those, imposed on the whole universe rather than on its neighborhoods, may block the construction. But look at what you have just done. The entire content of the theorem is that we have no idea what the global structure of the universe is like. Defeating it, by assuming a global property, is not an answer. It is the thing under dispute, asserted. And so the question returns, in a form considerably more uncomfortable than when we first met it. Where does that come from? It does not come from empirical data. No data has been gathered about the regions we cannot see, by definition. It does not come from local induction. That has already been granted, in full, and it was not enough. So where is it coming from? What it is coming from is an assumption about the way you would like the universe to be, and that is the move the theorem makes. Elegantly and quietly. It does not claim to prove that we cannot know. It shifts the burden onto anybody who claims that we can, and asks them to say where their global assumption came from. Nobody has a good answer. Now let me sit with what this actually means for a moment, because I think it is the hardest thing in the whole subject, and it is easy to slide past it. Most of us carry a picture of scientific progress that looks like a slow accumulation. Every generation gathers more evidence than the last. The picture fills in, gaps close. And if you extend the line far enough, 1,000 years, 10,000, a civilization with instruments we cannot imagine and patience we do not have, the picture completes. Maybe not in our lifetimes, but in principle, given time, the universe is the kind of thing that yields. This says otherwise, and it says it in a very particular way. It is not, we have not gathered enough data yet. It is not, our instruments are too crude. It grants you every observation that any observer could make at every event in the entire history of the universe, past and future, and then grants you every local inference you are entitled to draw from them. And the answer is still no. The accumulation converges. It converges on something that is not the picture, and no further accumulation moves it, because there is no further accumulation. You already have all of it. Surely, though, simplicity helps? Occam's razor. Of the universes consistent with the data, prefer the simple one over the baroque one, and the ragged cut-and-paste chain loses to the clean geometry every time. Manchak's answer to this is honest and slightly deflating. He is not aware of any way to make that rigorous here. There is no natural property of simplicity showing up in this setting that would be useful to apply. You could try. Maybe somebody will. But as it stands, simplicity would have to be inserted into the theory choice as a non-empirical, essentially metaphysical criterion, pushing you one direction rather than another for reasons that are not evidence. Which is, of course, the same move we found at the bottom of the maximality condition, wearing a different coat. He says he is interested in the idea. Nobody has made it work. And now I want to distinguish this from something it superficially resembles, because if I do not, the whole result collapses into a much older and much less interesting conversation. Philosophers have known about underdetermination for a very long time. Descartes wondered, in 1641, how he could know he was not being deceived by an evil demon. Pierre Duhem observed, in 1906, that for any belief you hold, given any data whatsoever, you can preserve the belief by adjusting your auxiliary assumptions. You may have to do drastic things, plead hallucination, assume your senses are broken, Suppose the whole thing is a simulation, but it is always logically available. Kyle Stanford has argued that the history of science is full of theories replaced by alternatives their proponents could not even have conceived of. All of that is real, and Manchak's own view of it is that it is fun to think about and fun to talk about, and he does not lose sleep over it, because it is not coming from our best scientific theories. That is the crucial distinction, and it is stated right at the top of his paper. There is one kind of underdetermination that requires you to revise or abandon your best physical theories in order to escape the data. And there is a completely different kind that arrives without renouncing anything, where you hold your best physical theory absolutely fixed, exactly as it is, in perfect working order, and the predicament falls out of the theory itself. The first kind is a philosopher's puzzle. The second kind is a physical result. This is the second kind. It is worth adding that Manchak goes out of his way to say he has no stake in the larger philosophical fights this material could be recruited into. Indistinguishable spacetime arguments have been used to support all sorts of grand positions about realism and the aims of science. Bas van Fraassen and Clark Glymour both put them to work in books published in 1980, and Manchak notes in a footnote that he is interested in the implications but has no special commitment to any of those projects. His motivation, he says, came from simply considering the observer's situation inside our best large-scale physical theory. That restraint is part of why the result carries. He is not arguing for a worldview, he is reporting what the mathematics does. So we now know something we did not know 2 hours ago, if you have been with me from the start. We know that the global structure of the universe cannot be determined by evidence, that the natural objection fails, and that the failure is not a philosophical trick but a theorem. What we do not yet know, what I promised you at the beginning, and am not going to hand over early, is what that actually means for the biggest question in the subject, and why it makes that question the one that might never get answered. We are not ready. There are 3 more things to see first, and the first of them is the single, solitary exception the theorem allows. Let us step back for a moment and put the pieces together, because we have been building steadily, and it is worth seeing the whole structure before we go further. We started with a universe where time loops, handed to Einstein as a birthday present, which he could not find a reason to exclude. We found that Einstein's equation, standing alone, has no content, that the collection of models is enormous, and that choosing a subclass of it is choosing a theory. We found that the tools used for that choosing include an 18th century intuition about nature's temperament. We found that classical determinism is a property of the curated list, rather than of the world. We found a definition, observational indistinguishability, and a conjecture, sitting unproven for 3 decades. And we found that when the conjecture was finally proved, it came back stronger than anyone had asked for. Every universe except one peculiar type has a nemesis that is globally different, obeys every local law yours obeys, and produces every observation any observer in yours could ever make. Every universe except one peculiar type. That is where we are, and that is what I want to look at now, because the exception is one of the strangest objects in this entire subject, and I have been holding it back on purpose. The exception is a universe containing what we might call a God point. Technically, Manchak calls these spacetimes causally bizarre, and the condition is easy to state. A God point is an event whose past light cone is the entire universe. Everything that has ever happened anywhere is visible from that single event. Every star, every collision, every particle interaction in the history of the cosmos, all of it inside the observational past of one point. And when I say everything, I mean everything, which includes the future of that very point. Because if the past light cone of an event is the whole manifold, then the whole manifold includes the parts of the manifold that lie ahead of it, which means the geometry has to wrap. Follow your own past far enough, and you arrive at your own future. A universe with a God point necessarily contains closed time-like curves. It is not optional, and it is not an accident of the construction. It is forced by the definition. Stand there for a moment, because I think it is worth feeling. You are at an event, and you look outward, and there is no horizon, not a distant one, none at all. Every direction you look, the light arriving carries a complete report. You see the formation of the first stars, and the interior of every collapse, and the far side of galaxies that in any other universe would be permanently walled off from you. There is no edge to your knowledge. Nothing is hidden anywhere, at any time, in principle or in practice. The whole of reality is in view from a single spot, and you are standing on it. And then you notice, among the things arriving, tomorrow, and the year after, and the moment of your own standing here, seen from somewhere further along, arriving back at you as light. The universe that has withheld nothing has also withheld nothing about you. You are looking at your own future because it is part of everything, and everything is what you can see. That is the price. And once you see it, it is very hard to unsee. In every universe where the shape of reality is knowable, the shape of reality includes a path that returns. Total knowledge of the universe is available in exactly one kind of universe, one where time closes. You can have complete knowledge of the world, or you can have a past that stays behind you. General relativity, as far as anyone has been able to determine, does not offer both. There is a further wrinkle that makes the word bizarre feel earned rather than dismissive. If everything is visible from that point, then among the things visible is the observation itself, the act of looking, seen from further along the loop, arriving back, and then the observation of that observation. The regress does not terminate anywhere. It is not that the picture contains a surprising item, it is that the picture contains itself, all the way down, and there is no outermost frame. That is a genuinely different kind of object from a universe that merely happens to be transparent. It is also worth naming the technical object underneath all of this, because it has been quietly doing the work for the last hour. In this literature, the observational past of a point is written as a specific set, all the events from which a time-like curve reaches that point. That set is the formal stand-in for everything you could possibly have observed by the time you arrive at that moment, your complete evidential situation, rendered as a region of geometry. The whole subject consists of comparing those regions. Two universes are indistinguishable when their observational pasts match up. A universe is causally bizarre when one of those regions swallows the entire manifold. Every result we have looked at tonight is a statement about the shapes of those sets and how they fit together, which is a slightly astonishing thing to say about questions that sound as though they belong to philosophy. Manchak uses this as a minimal background condition in his work. Restrict attention to spacetimes without God points, then prove theorems. And his reason for the restriction is purely practical. If you do have a God point, then a lot of the unknowability material simply does not go through, because you have access to everything. It is an exclusion clause. 4 words of housekeeping in a technical paper. But look at what the exclusion clause describes. It describes, in the language of differential geometry, exactly the vantage point that every theological tradition has attributed to an omniscient observer, a single point from which all of creation, in all of its moments, is simultaneously present. And general relativity says that such a vantage point is geometrically possible. It does not forbid it, it merely notes that in order to have one, the causal structure of your universe has to do something we would otherwise call pathological. I want to be careful here and not overreach, because this channel is in the business of wonder rather than metaphysics, and it would be very easy to inflate that observation into something it is not. It is not evidence for anything. It is a coincidence of language and geometry, and coincidences of that kind should be enjoyed rather than argued from. But it is a real coincidence, sitting in a real paper, and I find it hard to walk past. One clarification before we move on, because the two ideas are easy to confuse. Gödel's universe is not itself a God-point universe. It contains closed time-like curves through every event, which is a different and weaker property. Time travel is necessary for a God point. It is not sufficient. There are universes riddled with time loops in which observers still cannot see everything, and those universes are still covered by the theorem. So the exception is narrow, and it is bought at an enormous price, and it is almost certainly not us. Which leaves us where we were, but with something new to consider. Because if a universe can contain a point that sees everything, what else can a universe do, simply by being the right shape? What other work can geometry be made to perform? The answer turns out to include solving a problem that mathematics proved, 90 years ago, has no solution. In 1936, Alan Turing proved that there is no general procedure for deciding whether an arbitrary computer program will eventually stop running. You can run the program and watch. If it halts, you know it halts. But if it has not halted yet, you never know whether it is about to, or whether it will run forever. And Turing showed that no cleverness fixes this. No algorithm exists that takes any program as input and correctly answers, in finite time, whether it terminates. It is called the halting problem, and it is one of the hardest walls in all of mathematics. There is a shape of spacetime you can sit in that walks straight through it. The object is called a Malament-Hogarth spacetime, and the definition is short. It is a spacetime containing an event whose past light cone contains the entire infinite future of some other observer. Read that again slowly, because it does not sound possible. You are at a single point, a specific place, a specific moment, a finite spot in your own life. You look, and among the things arriving in your light at that moment is the complete, unending future of somebody else. Not a long stretch of it, all of it. Their whole infinite history is inside your finite present. Now put a computer on that infinite world line. Program it to work through some problem and to send you a signal if and only if it halts. Then go and sit at the special event and wait a finite amount of time, an hour, a year, whatever the geometry requires. If a signal arrives, the program halted. And if no signal arrives by the time you have passed the relevant point, the program never halts, because you have just watched an eternity go by and it never did. You have decided the halting problem, not by computing faster, not by finding a cleverer algorithm. None exists. That was Turing's whole point. You did it by sitting in the right shape of space and time. The machine is not made of components. It is made of geometry. The name has a story attached, and it is a small piece of academic history I find rather touching. The idea was David Malament's. He never published anything about it. He was in correspondence with John Earman and a few others about the possibility, and the idea circulated in letters. The first person to actually publish a paper on the construction was Malament-Hogarth in 1992, asking in his title whether general relativity allows an observer to view an eternity in a finite time. So John Earman proposed a compromise. Call them Malament-Hogarth spacetimes, and the main theorems about them, including the result that such a spacetime is necessarily not globally hyperbolic, no Cauchy surface, no complete instant, are also Malaments, a whole class of exotic geometry named half after a man who never wrote about it in print. Now, the objections. There are several, and they are not frivolous. The first and best is the blue shift problem. When the computer out on the infinite world line sends its signals back toward your finite receiving point, those signals bunch up. An eternity of transmissions has to fit into your finite weight, and so the received frequency climbs without bound. Wavelengths run toward the blue end of the spectrum, and then straight past it. The signals become unreliable, and then they become something with no sensible physical description at all. Some people say this makes the whole construction physically unreasonable, and Manchak's own view is that he agrees with that criticism. There are others. Are the standard energy conditions satisfied? Would the computer have to accelerate wildly to traverse the required path? Would it need infinite fuel to do so? Each of these has been raised as a reason the construction cannot describe anything real. John Earman and John Norton assessed the whole family of objections in a paper in 1993, with the very good title, Forever is a Day. And Manchak's response to all of this is the thing that tells you most about how he works. He collects them up. All of the reasons people want to exclude these spacetimes, blue shift, energy conditions, acceleration, fuel, assembled into a list, and then he goes, in his own phrase, into his little workshop and builds a model, a Malament-Hogarth spacetime, with none of those properties. It satisfies the energy conditions. It is stably causal. It is, in the ways the objections care about, well behaved. Every objection on the list, answered by construction. And then he says, the thing that makes the work honest, and that a less careful person would have left out. The irony is that this model is pretty unphysical, even by his own standards. That is not a failure. It is the entire point, and it is worth understanding clearly, because it is how this kind of mathematics actually functions. The model is not a proposal about our universe. Nobody is claiming we live in one. It is a counterexample to a line of reasoning, and the line of reasoning goes like this. Malament-Hogarth spacetimes cannot possibly happen because they have unphysical property X. To which the reply is, here is one without property X. So if you have some other reason, I would be glad to hear it, but the reason you gave is not enough. The ball goes back across the net. Somebody has to serve again. Which is the same request Einstein made in 1949. Find me a reason to exclude this on physical grounds. 77 years on, the request is still being made, still politely, and still nobody has produced the reason. What has been produced instead is a very long series of partial answers, each of which turns out, on inspection, to be a preference dressed as a principle. There is a logical relationship here that deserves a moment, because it inverts what you would expect. If a spacetime contains closed time-like curves, then the Malament-Hogarth property automatically holds. Time travel gives you eternity in a finite time for free. But the converse fails. A Malament-Hogarth spacetime need not contain any closed time-like curves at all. Which means that of the two, the eternity machine is the easier one. Time machines are much harder to build than Malament-Hogarth machines, and we have a considerably better grip on the latter. And they are not confined to bespoke constructions either. Anti-de Sitter spacetime, the negative cosmological constant geometry that anchors a great deal of modern theoretical physics, is a Malament-Hogarth spacetime. So, in the relevant region, are the interiors of rotating and charged black holes, as you approach the inner horizon, which means the blue shift objection and the Cauchy horizon instability question that cosmic censorship is about are, in the end, the same physics looked at twice from different directions. There is one more piece, and it is the cleverest thing in this part. John Earman proposed a way of thinking about machines in general relativity that gets around the fact that you cannot say which extension of a spacetime will actually occur. Evolve your data as far as it goes. Reach the point where extension becomes non-unique, where the theory offers many continuations and no way to choose. You cannot say which one obtains. But suppose you could prove that every single one of them, without exception, has some property. Then you do not need to know which one happens. Whichever it is, the property holds. You have built a machine that produces it. Manchak did exactly this for the Malament-Hogarth property. He exhibited globally hyperbolic spacetimes that cannot be extended any further while staying globally hyperbolic, so they have many non-unique extensions, and showed that every last one of those extensions is Malament-Hogarth, which is a strange and marvelous kind of certainty. You cannot know what the universe will do, but you can sometimes know what all of its options have in common. The The literature that grew around Ehrman's idea is unusually eventful, and I mention it because it says something honest about how this subject proceeds. Several theorems in the time machine literature have, over the years, been proved false by various people, not disputed, falsified, results that were published, believed, and cited, and then shown to be wrong. Manchak himself has a paper in that tradition, with the very dry title, No No-Go, arguing that the proposed no-go results against time machines do not establish what they have been taken to establish. Itamar Pitowski had raised closely related ideas about computation and spacetime a couple of years before Hogarth's paper appeared, in 1990. This is a small field where the arguments are genuinely difficult, and where people are willing to say in print that the previous answer was mistaken. That is what a healthy corner of a science looks like from the inside. Hold that thought, because in a moment, somebody is going to use exactly that trick to answer a question that had been sitting open for half a century, and the tool they use to do it is a shape with infinitely many holes in it. More than 50 years ago, Robert Geroch asked a question that sounds like a riddle and turns out to be a knife aimed at one of the assumptions we looked at earlier. The question is this. Suppose you have a spacetime that is extendable, not as large as it could be, capable of having more universe attached to it, and suppose that as it stands, it contains no closed time-like curves at all, no time travel, perfectly well-behaved causal structure. Now, can you find one where every single extension of it contains closed time-like curves, where the universe cannot grow, in any direction, by any amount, without opening a loop in time? Remember what Maximality said. Nature does not stop when nature could keep building. Extendable universes are physically unreasonable, because a universe that could have been larger and simply is not, offends our sense of how nature behaves. If Geroch's question has a positive answer, then somewhere in the catalogue of models, there sits a universe with a genuinely awkward choice built into it. Stay this size and be unreasonable in one way, or grow and be unreasonable in another. Not a paradox, just a place where two of the criteria we use to sort the debris from the universe's point in opposite directions. Manchak carried that question around for roughly 10 years without solving it. He had a sketch. Take Minkowski spacetime, flat, empty, the simplest geometry in the subject, and roll it up in the time direction, the way you would roll a sheet of paper into a cylinder, except you are rolling time. Now every world line closes. The whole thing is time travel, everywhere. That is the crude starting material. And then remove a fractal. Specifically, a Cantor set. The object Georg Cantor described in 1883, built by taking an interval and repeatedly removing the open middle third of whatever remains, forever. What is left has zero length. It occupies no space at all in the measure-theoretic sense, and yet it contains uncountably many points. It is totally disconnected, nowhere dense, infinitely fine, and infinitely full of gaps. It is one of the most delicate objects in mathematics. Poke a pattern of holes shaped like that into the rolled-up space-time, and the holes block the closed, time-like curves from forming. Every path that would have wrapped around now runs into a puncture. The time loops cannot close, because there is always a missing point exactly where they would have needed to pass. But the structure is so delicate that any attempt to extend the space-time, to grow it in any direction, requires extending a bit of that fractal, and extending the fractal means filling in some of the gaps, and filling in a gap opens a little path for the closed time-like curve to form. That was the idea. He mentioned it, more or less in passing, to a group of mathematicians in Budapest, the Logic Group at the Alfred Rényi Institute, who have spent decades building axiomatic, model-theoretic foundations for relativity theory, coming at the subject through logic rather than differential geometry. He said something like, "If you can see a way to do this, here is an idea." They went to work, and they did it. The paper, by Hajnal Andreka, Judith Madaras, J.B. Manchak, Istvan Nemeti, and Gergely Seykeli, settles Geroch's question. It appeared as a preprint in October of 2025 and was published in Foundations of Physics, Volume 56, in 2026. A question posed more than 50 years ago, answered by removing a shape with no length and uncountably many points from a universe that had been rolled into a cylinder. It is worth being precise about what that costs the maximality dogma, because this is the Pandora's box we opened earlier, arriving with a concrete example in hand. Geroch's own theorem, from 1970, says every spacetime has a maximal extension. That theorem is true relative to the standard collection, but it is proved using Zorn's lemma, an existence result rather than a construction, which tells you that something is there without ever showing it to you. Now take the new spacetime. It has no closed time-like curves. It is extendable. If you insist that physically reasonable universes must be maximal, then this universe must grow. And if it grows, in any direction, by any amount, it acquires time travel, which the same tradition has spent 77 years trying to find a reason to exclude. So here is a single object on which two of our criteria for physical reasonableness disagree. It cannot satisfy both. Nothing about the field equations resolves the disagreement, because the disagreement was never in the field equations. It was in the criteria we brought to them. I want to stay with the human side of this for a minute, because I think it is the most instructive thing in the whole 2 hours, and because it is the opposite of the story we usually get told about how discoveries happen. Manchak describes himself as very slow. He is not being modest. He says things do not come quickly to him, that he has built this understanding over the course of 20 years, that he is not comfortable in the kind of conversation where physicists and philosophers spar in real time about ideas. He is not the person who wins the argument at the seminar. What he identifies as his one real strength is this: he does not give up on an idea. Where somebody else would set a problem down and move to something more tractable, he comes back to it, and back, and back. For years, he held the question of what makes a manifold physically reasonable for 2 decades. He held Geroch's question for about 10. The work itself looks like almost nothing. There is a clipboard, one of his cherished possessions, always with paper on it, and a mechanical pencil. Much of this material lends itself to pictures, and he thinks in pictures. That is how the theorems get proved, by drawing the thing, and drawing it again, and going back over it, and if it is not there that day, coming back the next day, and walking to and from the university, and, yes, the shower, like everyone else. He is candid that the habit has a cost. It is incessant, he says. He cannot help it. Almost destructively so. It is hard for him to sleep sometimes. It pulls him out of conversations he should be paying more attention to, because he is somewhere else, turning something over. These days he does not work alone, and he clearly prefers it that way. He writes papers with collaborators by text message, going to sleep thinking about some question concerning symmetry and structure, texting the idea over in the morning, getting a reply back. He calls Thomas Barrett his symmetry buddy, and describes the arrangement with obvious affection. The first part of his career he wrote everything by himself, and having people to bounce ideas off is, in his words, so much better. His co-authors on this material include Barrett, James Weatherall, and Hans Halvorsen, all of them working in the style that traces back to Malament. And when he was asked what he would tell his younger self, the answer was not about technique or about choosing better problems. He has an 11-year-old daughter, and it is what he says he is trying to teach her. Do not give up. Keep going. Keep trying. Other people will stop at this stage, or at that one, and it makes a very large difference if you simply do not. That is what produced the strongest result anyone has about the limits of knowing the shape of the universe. A clipboard, a pencil, 20 years, and an inability to let go. Now, Everything we have seen so far has pushed in one direction, toward the conclusion that the global structure of the universe is beyond determination. It is time to turn around, because there is exactly one known way through the wall, and it was found by the same man who built the wall, and it is the strangest idea in this entire subject. Around 500 years before the Common Era, in the Greek city of Ephesus, a man named Heraclitus wrote a book that has not survived. What survives are fragments, quoted by later authors, and an idea that everything flows, that nothing stays, that the world is not a collection of things, but a process that never repeats. The line everyone knows comes to us through Plato: "You cannot step into the same river twice." It is usually read as a remark about impermanence. It is not only that. The claim is sharper than melancholy. It is not that the river is gone. It is that there was never a second instance of anything, that no two moments in the world have ever been the same moment in any respect that matters. Early on tonight, when we had nothing but a bare manifold, I said that such a universe would be a river you could step into as many times as you liked, and it would be the same river every time, because there would be nothing about it that could ever differ. Every point exactly like every other. Perfect featurelessness. Now put the metric back on, and go all the way in the other direction. A Heraclitus spacetime is a universe in which any two events you pick are different in some way. That is the entire definition, and you do not need any general relativity to state it. Choose any two events in the whole history of the universe: a photon scattering in a nebula, a wave breaking on a beach 4 billion years ago, and there is something about the local structure at one that is not true at the other. No two neighborhoods anywhere in space and time are alike. The technical version is tighter and worth hearing. For any two open regions of the spacetime and any isometry from one to the other, any map carrying the geometry of one exactly onto the geometry of the other, it follows that the two regions were the same region all along, and the map was the identity. There are no non-trivial local symmetries anywhere in the universe. Every patch is unrepeatable. Now, a sharp listener will have an objection ready, and it is the right objection. Did we not establish, hours ago, that the defining property of a manifold is that near any point it looks flat, and that every point is like every other? How can the local structure differ from place to place? Because general relativity does not work with the bare manifold. It works with the metric on top of it, and the metric can differ from point to point. In a Heraclitus spacetime, each point has its own geometry, its own curvature, its own particular character. The manifold underneath is as featureless as ever. The structure laid on top of it is different at every single event. There is a related thing people say, and it is a misconception worth correcting directly, because it sounds so authoritative. People say that locally, every point of spacetime looks like Minkowski space. In the sense being used here, that is not true. Minkowski spacetime is flat. Its curvature quantities vanish identically at every point. In an arbitrary spacetime, curvature varies from place to place, and any map claiming that 2 points are the same has to preserve all of that curvature structure. What the Heraclitus construction does is examine precisely those curvature properties and demand that no 2 points share the whole set of them. And here is where it turns around on everything we have built tonight. Because in a Heraclitus universe, local structure determines global structure, and the unknowability collapses. Picture this. Somebody hands you a box. Inside the box are pieces of a universe, a space-time cut up small, thousands of fragments, and you are asked to reassemble it. You are not told which universe it was. Run it first with Minkowski pieces. Every fragment is identical to every other fragment, because every point of Minkowski spacetime is identical to every other point. You start fitting them together, and they fit. They fit everywhere. Any piece goes next to any piece. And when you finish, you have built flat, ordinary Minkowski spacetime. Or, You have built a rolled-up Minkowski spacetime, with time running in circles. Or, you have built a Minkowski spacetime with a hole torn out of the middle of it. A singularity where nothing caused one. All three are legitimate assemblies of exactly the same pieces. There is no fact about which one was in the box. Now run it again with Heraclitus pieces. You pick up a fragment, and it is strange, jagged in a way nothing else is jagged. You look for its neighbor, and there is exactly one piece in the entire box that fits against that edge. One. And on the other side, one. And on it goes. Every edge in the universe admitting exactly one partner, the whole thing locking together in a single, unrepeatable arrangement. There is one way to assemble it, only one, and when you are done, you know what universe you are in. So Manchak, having proved that we cannot know the shape of the universe, went on with Thomas Barrett to identify the precise condition under which we can. He describes writing that paper as arguing against himself, which he found a strange thing to do, and he treats the result not as a refutation, but as a demonstration of his own theorem's limits. Every theorem has limits. This is where his are. The accounting is exact, and it matters. The theorem breaks only because he had been proving it with the most liberal notion of a local property he could construct. Constrain local inductions to the ordinary things, energy conditions, vacuum solutions, the sort of assumption a working physicist actually makes, and the theorem goes through completely unharmed. It is only under the maximally permissive reading of local structure, in a radically asymmetric universe, that the local quietly smuggles in the global. And now the part that reorganizes everything. Manchak believes almost every spacetime is probably Heraclitus. The reasoning is not about relativity in particular. Take any kind of mathematical structure at all, a set, a topological space, a manifold, and look at the space of all objects of that kind. A randomly chosen one will generically have no symmetries, none. Symmetry is not the ordinary condition of mathematical objects. It is the rare exception. And we notice it because it is rare and because it is useful. So why has nobody ever shown you one? Because they are extremely hard to write down. To study a space-time by hand, you need symmetries. They are what make the equations tractable, what let you reduce a four-dimensional problem to something a person can hold. Open any textbook on general relativity, and every model in it was chosen because it was simple enough to work with. Schwarzschild is spherically symmetric. Minkowski is symmetric under everything. The cosmological models are homogeneous and isotropic by assumption. Which means the entire canon, every spacetime any of us has ever been shown a picture of, is a curated exhibit of atypical cases. Not because anybody was hiding anything, because those are the ones you can draw. The model Manchak and Barrett actually built is disarmingly modest. 2 dimensions, one of space, one of time, made conformally flat, so it has the same causal structure as ordinary Minkowski spacetime, and then 2 curvature functions, call them P and Q, tuned so that 2 points may share the same value of P or the same value of Q, but never both at once. That is enough. That is a universe in which nothing ever repeats. He found it by playing. As a mathematics graduate student, he had written code that took a space-time metric as input and returned its curvature quantities, and he sat with it, feeding in metric after metric, watching the curvature properties, trying to get them to interlock. The theorem came out of experimenting with a program. There is a follow-up result, published in the Journal of Philosophical Logic in 2024, on Heraclitus maximal worlds, universes as large as they can be, while keeping the property. Those require Zorn's lemma, which is a form of the axiom of choice, and it is worth heading off the objection that this makes the whole thing an abstract artifact. Zorn's lemma is standard for maximality results in this subject. Geroch's own maximal extension theorem uses it. And for the plain Heraclitus property, No choice principle is needed at all. Manchak can simply write the metric down and hand it to you. And there is one more casualty, which was never the point of the exercise, but which fell over anyway. For decades, philosophers of physics have worked with a rule of thumb connecting symmetry to structure. The more symmetries an object has, the less structure it carries. The fewer symmetries, the more structure. It is intuitive. Add a marker for the center of the universe, and you can no longer shift everything 4 feet to the left, so structure went up, and symmetry went down. John Earman laid out a whole ladder of classical spacetimes on exactly this principle, each rung adding structure, removing symmetries, and making more questions about motion meaningful. Until, at the top, it makes sense to ask how fast you are going in absolute terms. The Heraclitus results throw a wrench into it. Asymmetry maxes out. You cannot be more asymmetric than a universe in which no two events are alike. There is nothing left to break. But structure does not max out. You can keep piling structure on top of a Heraclitus spacetime indefinitely, adding markers and fields and distinctions, and the symmetries do not decrease, because there were none to begin with. The two quantities come apart at the extreme, and a rule of thumb that held up for decades turns out to have been describing the middle of the range. None of which, I should say immediately, sounds like good news for cosmology. If our universe really is one where nothing repeats, what happens to the models built entirely out of the assumption that everything does? The standard models of the universe are built on two assumptions, with names that sound gentler than they are. Homogeneity. The universe is the same everywhere. Isotropy. It looks the same in every direction. Together they are called the cosmological principle, and the whole family of models named for Friedman, Lemaitre, Robertson and Walker rests on them. They are enormous symmetry assumptions. They were adopted long before there was any evidence for them, largely because without them, the equations are not solvable by hand. A Heraclitus universe has no symmetries at all. So which is it? The answer is about scale, and once you see it, the tension dissolves. The Heraclitus claim applies when you zoom all the way in. It is a statement about the very particular curvature properties of individual events, that no two of them agree on every last one. The cosmological models zoom all the way out. At that scale, one talks about approximate symmetries, and there is serious work by both philosophers and physicists making that notion precise. On this picture, a homogeneous isotropic model is an approximation to some underlying geometry that is Heraclitus all the way down. And when you are studying the universe on scales of hundreds of millions of light-years, the tiny differences in curvature between one point and another simply do not matter for what you are trying to model. Manchak sees no contradiction and no tension whatsoever. You just have to keep track of what you are studying and what you are trying to model. The assumptions are excellent as long as you understand what you are doing with them. The problem arrives only when somebody bangs a fist on the table and insists that a homogeneous, isotropic model really is an accurate representation of our universe, because it visibly is not. There are clumps of galaxies here and not there, filaments and walls and voids running to hundreds of millions of light-years. Our universe is not completely homogeneous, and it is not completely isotropic, and everybody in the field knows this perfectly well. The models are tools, applied at a scale where the approximation holds, and there is nothing wrong with that, unless you forget it. The same goes for the broader worry, which is whether science itself survives a universe where nothing repeats. Science is supposed to require repeatability. If no two events are ever the same, what happens to that? It survives comfortably, and the reason is a detail in the definition that is easy to miss. In a Heraclitus universe, two events are not different in every respect. They are different in some respect. That is all the condition requires. Both events still sit on a manifold, and the manifold structure at each is identical. Both still have a light cone. The causal structure is very similar. Many curvature properties may well be shared. The only thing forbidden is that everything match, which leaves enormous room for induction over all the other properties, and induction over shared properties is what science actually does. You could even put Heraclitus-style data on a surface with every point slightly different from every other, and evolve it forward using exactly the classical theorems we looked at earlier. It presumably all works out. Manchak's assessment is that it does not limit science at all, that all the theorems everyone knows and loves are presumably intact. The only real cost is that these spacetimes are hard to study, precisely because they lack the symmetries that make analysis possible. And it is worth dissolving the repeatability worry properly, because it rests on a picture nobody has ever actually held. Repeatability in practice requires that two experiments agree in the respects being measured. It has never required that two moments of the universe be identical in every respect. Nobody has ever run an experiment twice in an identical universe. The second run always happens later, somewhere else, in a slightly different gravitational field, with the Earth in a different place. We have always been doing science in a world where nothing repeats exactly. We just did not have a name for it. There is one further worry worth answering, because it is the natural one for anyone who has spent time with cosmology. If a universe is maximally asymmetric, does that not smuggle in a preferred direction, or a center? Exactly the things the cosmological principle was designed to rule out. Manchak thinks it goes the other way. A spacetime implicitly defines geometric structures on itself, when those structures are preserved by its symmetries. That is how a symmetric universe picks out a small family of natural fields and rules the rest out. Strip away every symmetry, and nothing is picked out. All sorts of geometric structures become compatible with the geometry at once. The situation opens up, rather than narrowing toward a preferred anything. There is one honest open question in the vicinity, and I want to flag it as open rather than settled. It is whether small-scale structure really does average out cleanly at large scales, or whether the averaging introduces corrections nobody has accounted for. In cosmology, this goes under the name of the back reaction, or averaging, problem, and it is a live area of research. Asked directly whether integrating out the fine structure could go wrong, Manchak's answer was that he is not aware of any problem and would guess not. That is a guess from someone careful enough to label it as one, and it should be received that way. Now, since this material circulates, let me deal with what tends to be made of it. The first thing people do with underdetermination results is announce that physics has admitted it is all made up. If scientists cannot determine the structure of the universe, then scientific claims about the universe are arbitrary. This gets the result backwards in both directions. The theorem concerns global structure only, the large-scale shape and topology of spacetime beyond what any observer can see. It says nothing about local physics, which is exactly the part confirmed to extraordinary precision every day of the week. The magnetic moment of the electron is measured and predicted in agreement to more than 10 decimal places. Navigation satellites carry relativistic corrections of 38 microseconds a day and would be useless within hours without them. And the theorem requires general relativity to be correct in order to work at all. A result that presupposes a theory is not evidence that the theory is arbitrary. The second thing people do is reach for the simulation hypothesis. If the evidence cannot rule out radically different universes, perhaps the universe is a construction. But we have already seen why this is a different animal. There are two kinds of underdetermination. The first, demons, hallucinations, simulations, requires you to abandon or heavily revise your best physical theories, and can always be sustained by adjusting auxiliary assumptions. It is fun to think about, and it does not keep anyone awake. The second kind requires no revision at all. You hold general relativity exactly as it is, in perfect working order, and the predicament falls out. Conflating the two throws away the only thing that made the second one interesting. The third thing because closed time-like curves keep appearing, is that time travel is being covered up. What is actually on display is the opposite of a cover-up. The models are published, taught, catalogued, and argued over in the open, and the disagreement about whether to exclude them has been conducted in public since 1949. The truth is stranger than the conspiracy. What the geometry permits is not changing the past, but a path that closes, and nobody has found a reason to rule it out, not because it is hidden, because it is hard. So cosmology stands. Physics stands. What does not stand is a particular kind of confidence about the whole, and we are almost ready to say exactly what that confidence was. Almost. There is one more room to walk through first, and it is the smallest one, and it is the one you are sitting in. Manchak teaches an introductory philosophy of science course, and the way he has built it tells you something about how he thinks. The class opens with the basics: logic, evidence, the general problem of underdetermination. Then it takes a case study, and the case study is physics, the cosmic underdetermination we have spent the night on, the shape of the universe, the theorem. And then, at the end of the term, it takes a second case study. The second case study is you. Here is the parallel, and I want to lay it out carefully, because it is the part of tonight where it would be easiest to overclaim, and the person whose work this is refuses to overclaim, and I am not going to do it on his behalf. David Hume was an empiricist. His method was to ask, of any idea, what observation it came from, and if no observation could be found, to treat the idea with suspicion. His most famous application of this was to causation. He watched one billiard ball strike another. He looked for the cause. And he found, try as he might, that he could see the first ball moving, and the contact, and the second ball moving, and the constant conjunction of the two across every case he had ever witnessed. But he never saw the causing. There was no observation of the necessity. The idea of causation turned out to be a slippery, metaphysical thing that no experience delivers. Then he turned the same method on himself. Try it, gently, since you are lying there anyway. Go looking for yourself, not for your name or your history or your body, for the thing that is doing the looking. Go inward, the way you would go into a room and see what is there. There is warmth or the lack of it. There is the weight of your body against the bed, which you were not attending to a moment ago, and are now. There is a sound somewhere, a fan, traffic, the small settling noises of a building at night. There is a thought about tomorrow that arrived without being invited. There is an ache in one shoulder. There is the awareness of the room, and the awareness of this voice. And you keep going, because none of that is what you were looking for. Those are things you have. You were looking for whoever has them. So you go further in, past the sensations, past the thoughts, toward the one who is noticing. And there is another sensation, another thought, another noticing. It is not that you find an absence. An absence would be something. It is subtler and more slippery than that. It is that the thing keeps not being where it obviously should be, and every time you arrive, what you find is one more perception. Hume's report is that when he entered most intimately into what he called himself, he always stumbled on some particular perception, heat or cold, light or shade, love or hatred, pain or pleasure. He could never catch himself at any time without a perception, and he could never observe anything but the perception. It is worth knowing that this frightened him. He came back to the problem in an appendix to his own book, and confessed that his account of personal identity did not work, that when he tried to explain the principles uniting our successive perceptions, he found himself in a labyrinth he could not escape, and that his hopes vanished. And in the body of the same work there is the famous passage where he describes what he does about it. He dines, he plays a game of backgammon, he converses and is merry with his friends, and after 3 or 4 hours of amusement, these speculations look so cold and strained and ridiculous that he cannot find it in his heart to enter into them any further. That is one of the most human paragraphs in the history of philosophy, and it is worth remembering that the man who wrote it had walked into the same shape of problem we have been circling all night, found it genuinely distressing, and went to play a board game. Now, the other tradition. Manchak has practiced in the Zen tradition for many years, and he sees a parallel between what Hume found and the Buddhist teaching of non-self. The traditions are enormously varied, but a few principles run through them. Impermanence is one, and non-self is another. Look carefully for the self, and it is not found where it is expected to be. And here is where the honest version of the parallel matters, because there is a bad version circulating everywhere. The bad version says, Hume proved there is no self, and Buddhism agrees, therefore science has validated ancient wisdom. That is not what either of them says. Hume was making an epistemological claim, a claim about what he could observe by introspection. It does not obviously follow that the thing he could not find does not exist. It is entirely consistent with introspection simply having systematic blind spots. Someone put exactly that objection to Manchak, in more or less those words, and his answer was not to defend the inference. It was to say that a Buddhist should not be understood as someone grasping onto the idea of non-self in the first place. That is a subtler position and worth sitting with. In the Zen tradition, as he describes it, non-self is not a doctrine you hold. It is a letting go of the idea of self, a refusal to grasp foolishly at something beyond your direct experience, or beyond the data you actually find yourself with. It is a way of being in light of a kind of underdetermination rather than a claim about what is or is not there. And it is characteristic of that tradition that if a student announced they had worked it out, that Buddhism is about non-self, the reply would be that they had missed the entire point, because grasping at anything, including the negation, is the thing being let go of. There is a related image in that tradition, of the finger pointing at the moon. The words are only the finger. Whatever they are pointing at is not in the words, which is a slightly funny thing to find at the end of an evening spent with a man whose entire professional style is to make things precise, and he knows it. He is explicit that any time you try to put this sort of thing into words, you are almost certainly going to get it wrong, and he is not a guru and does not present himself as one. His root there was ordinary. He grew up in a religious household, lost that in graduate school but kept the part of himself it had occupied, and remembered an undergraduate philosophy professor who talked about meditation. Then came the years of working extremely hard, the years where getting tenure took up nearly all the room in his head, and when he got it, there was suddenly space and a wish to calm down a bit. There happened to be a group sitting zazen in the neighborhood. He walked down the street and joined them. It has been part of his life ever since. Every night before bed, the whole family gathers in his daughter's room. His wife, his daughter, the dog, all of them on the bed together, and they sit for a moment. He describes it as a framework and a structure, which is what he wanted and what he needed. And there is one more piece of honesty required here, which is that Manchak himself does not claim a direct relationship between the two cases. Asked whether the unknowability of the universe's global structure has any bearing on the first-person situation, his answer was that he does not see a connection, only that there are limits in both places, and that the rough contours of the two predicaments look similar. Completely different contexts, similar shape. That is all it is. And I think it is enough. Two cases, a few centuries, and an entire subject apart, in which somebody gathered every observation available, and found that the observations did not determine the thing they were observations of. In one case, the thing was the shape of the universe. In the other, it was whoever is lying here in the dark, going looking. Which brings us, finally, to the question I promised at the beginning, and which it is now time to answer plainly. So, the greatest mystery in modern physics. There are several candidates, and you have heard them all. How to reconcile quantum mechanics with gravity. What dark matter is made of. Why the cosmological constant has the value it has. What happens to information that falls into a black hole? Every one of those is a genuine mystery, and every one of them is hard in a way that has humbled extraordinary people for decades. But they are all hard in the same way. They are hard the way a mountain is hard. They are waiting on an idea nobody has had yet, or an instrument nobody has built yet, or a piece of mathematics nobody has invented yet. They are difficult, and they might take a century, and they might humble another 3 generations. But there is no argument anywhere saying they cannot be solved. The obstacle is us. The mystery I have been walking you toward all night is not like that. Here it is, plainly. What is the shape of the universe you are lying in? Not how large it is, not what it is made of. Its global structure, its topology, its overall geometry, the way it is put together at the largest scale. Is it finite or infinite? Does it close on itself? Does it have holes in it? Is it one connected sheet or something stranger? Is there a boundary out there? Does anything anywhere in it permit a path that returns to where it started? That is the question. And it is the most natural question a human being can ask about the universe. It is the question every child asks in some form, the first time somebody tells them the sky goes on. It is older than physics. And when you take our best, most confirmed, most extravagantly successful theory of space and time, and you put that question to it directly, the theory answers by proving that the question cannot be settled by evidence. That is why it might never be solved, not because it is difficult, not because the funding is not there, or the telescope has not been built, or the necessary genius has not yet been born, because general relativity itself, from inside, using nothing but its own mathematics, holding every one of its assumptions perfectly fixed, proves that no observer anywhere, at any moment, in the past, or the present, or the future, gathering any quantity of evidence whatsoever, can determine which universe they are in, barring one exception, and that exception is a universe where time closes. The obstacle is not us. The obstacle is the theory, and a theory that tells you where its own answers stop is doing something that theories are not supposed to be able to do. Manchak has a phrase for this, and it is the cleanest summary of the whole evening. One can use science to show that science has limits. Notice how carefully that has to be said. Philosophy has been showing the limits of science for 4 centuries, and it has done it from outside, with demons and dreams and brains in vats and wild hypotheticals that require you to throw away everything you know in order to entertain them. That is a different move, and Manchak is explicit that it is not the one he is making. What he is doing is taking the theories of science seriously, completely seriously, exactly as they stand, following out their consequences, and finding the boundary written into the mathematics. He loves science. He does it every day. And what he is pointing at is that even in principle, there are things science will not be able to help us better understand. And in this case, one of those things is the large-scale structure of the universe we happen to live in. We have seen this pattern before, twice. In 1931, Kurt Godel showed that any formal system rich enough to do arithmetic contains truths it cannot prove. In 1936, Alan Turing showed that no algorithm decides whether an arbitrary program halts. Both were limitative results. A system examined rigorously, reporting on what it cannot deliver. And the same man who wrote the first of those handed Einstein a manuscript in 1949 and started a conversation that has now run for 77 years without ending. It has taken this long for us to notice that the third one was in the geometry all along, waiting, and that it took somebody slow and stubborn enough to go and check. Which brings back the phrase we have been carrying since the first minutes. Einstein asked whether such solutions ought to be excluded on physical grounds. It sounded like a routine request. Somebody go and find the reason. And what the 77 years since have shown is that every attempt to find that reason has come back holding a preference rather than a principle. Maximality resting on an intuition about nature's temperament, global hyperbolicity, smuggling in the answer it was meant to establish, simplicity, with no rigorous formulation to offer, and every global assumption meeting the same quiet question: where does that come from? It is worth being clear about what has not been lost, because I do not want you drifting off tonight thinking that physics has been taken away from you. It has not. Every local law stands. Everything we can measure, we can still measure, to the same absurd precision as yesterday. Cosmology works. The models are excellent tools used at the scale they were built for. What we have lost is only this: the assumption that if we kept going long enough, the picture would close. And in exchange for it, we got something. We got the pluralists' honest project. Stop asking which collection of models is the real theory, and start asking what follows relative to this one, and this one, and this one. We got a precise map of where the boundary sits, and a precise account of the one condition under which it lifts. Because there is a universe in which all of this dissolves. A universe where no two moments are alike, where every event carries its own unrepeatable geometry, where the pieces fit together in exactly one way, and the whole thing can be reconstructed from any handful of them. A universe that cannot be stepped into twice. In that universe, and possibly only in that universe, we could know where we are, and it may very well be ours. Nobody can tell us. And I want to be fair to the people who will read all of this and shrug, because that is a defensible position too. There is a deflationary version of tonight, and it goes like this: none of it is new in kind. Underdetermination has been a philosophical staple since Descartes. The results concern only regions we cannot see. Every working cosmologist already knew that claims about the unobservable universe are conjectural, and the theorem merely tidies an intuition rather than overturning anything. That is a reasonable reading, and some serious people hold it. The stronger reading, the one I find harder to argue away, says the difference is exactly the thing we kept coming back to. Every previous version of this argument required you to loosen your grip on the physics in order to run it. This one requires you to hold on tightly. It comes out of the theory, with the theory held fixed, and it survives every local inference you are entitled to make. That is not a philosopher's puzzle wearing a lab coat. That is a physical theory reporting on the shape of its own silence. So we are left holding the thing this channel is happiest holding, which is a genuine, well-mapped, honestly arrived at, we do not know, not a shrug, not a failure of nerve, a result. It took a birthday present in 1949, a conjecture in 1977, 4 pages in 2009, and a fractal in 2026 to establish it properly, and what it establishes is that the greatest mystery in modern physics, the actual shape of the universe you are lying inside of, right now, might never be solved, and that this is not our fault, and that we know it with the same confidence we know anything else in the theory. There is something almost restful in that, if you let it be. All night, people have been going to the window and looking out and trying to work out how far it goes. And it turns out that the not knowing is not a gap in the work. It is part of the shape of the thing. The universe is not withholding an answer from us out of difficulty. It simply is not the sort of object that an answer of that kind fits. Thank you for coming this far out with me tonight, into a question that does not close. If this is the kind of slow walk you like taking before sleep, a like or a subscribe would mean a great deal. It is what keeps these long nights possible. And remember, the next time you look up and wonder how far it all goes, that the wondering is the honest part. Good night, and may you never quite look at the edge of things the same way again.